Good afternoon. I'm Professor Sever. Today we're going to do an introduction to abstract vector spaces and subspaces. Let's review the example we discussed in the previous installment in this series. So W was a line in the plane, namely y equal mx, and we proved the following conditions: that the zero vector was in W, we proved the closure of the scalar product, and we proved the closure of the vector addition. So since W is a line in the plane, I thought we would take a moment to look at those proofs graphically before we went on to the next set of examples and before we reviewed the general process of proving that a subset is a vector space. First, we see the set W depicted graphically as the line y equal mx. And our first observation is that the origin is on the line, which is what we showed. We showed the zero vector, which is the origin in the plane, is in W. Next, let's look at a diagram that illustrates our proof that the scalar product was closed in W. So if we take a pair, we have it written here in blue, xy on the graph, and if we look at a scalar multiple, namely c times xy, it is also on the line, on the graph. We're visually representing how the closure would look in this particular case of the vector space W. Next, let's look at our proof that the vector addition was closed. So if I have two ordered pairs, x1, y1 and x2, y2 on the line, again I'm just drawing them anywhere for convenience. I'm showing that the sum x1 plus x2, y1 plus y2, that ordered pair, is always on the line. And I'm showing that here graphically. Now we will revisit the technique of proving that a subset is a subspace of a known vector space V. So again, we're saying the same thing for the third time, but we're kind of elevating it in prominence. So what we're saying is, how do we go about showing a subset W is a subspace of a vector space? We need to do three things. First, you need four technically. You need to show that it's actually a subset in a previously known vector space V. Usually that will come from the problem description of W. Then you need to show it's non-empty. I don't want to say the best way, one of the ways to do that, maybe a preferred way would be a better way to say it. A preferred way is to show the zero vectors in W. Then all you have to do is show closure of both operations. And again, these can be done at the same time. Showing that W is non-empty, I just discussed this in a roundabout way. The zero vector must always be in the space. We just proved that was a theorem we just looked at. And therefore, why not use that as the vector that you use to show that W is non-empty? It's oftentimes the easiest thing to do. Not always, but oftentimes. Showing that W is closed under scalar multiplication. Okay, what you need to do, you start with an arbitrary vector in W. And what that means is you use the generic description that you were given that describes W. Then you state what it means for W to be in there. W has certain properties. W, capital W, is defined by certain properties. It's the set of all vectors such that whatever. Okay? And if W is in there, that means this vector W has to satisfy those conditions. That's what you need to use to complete this proof. You choose an arbitrary scalar, then you show that C times W has that defining property. Okay? And if you can do this, you'd be done with the scalar multiplication bit. Again, this is an abstract set of rules because we don't know what W is, but we're speaking very generally. These are the steps that you would need to go through, and there'll be an illustration coming soon. And you do the same type of thing for the scalar addition. You start with two objects in W. Again, W1 and W2 have to satisfy the conditions of membership, namely the defining condition or conditions that define W. Then you show W1 plus W2 has those defining property or properties. And if you can do this, you've shown the addition is closed. And if you do all three of those things in either order, then you would have shown W as a subspace. So again, we're going to go revisit our original example. And by the way, this is the defining property. W is a set of all ordered pairs such that y is m times x. So 0, 0's in there, as I discussed. I take an arbitrary vector. I want to show that the scalar multiple of it, which is this, is in W. And here's the proof. As I illustrated, we take y equal mx. If xy is in W, then y is equal to mx. Then we say multiply both sides by c. Then c times y is c times mx, which is also m times cx. And then you could see this value is m times this value. That's precisely what this equation says. That says the ordered pair, cx, cy is in W. But of course that's the scalar multiple of c times xy. Therefore, the scalar multiplication is closed. And then you would do the same thing again with regard to the addition. So since x1, y1 is in W and x2, y2 is in W, x1, y1, and x2, y2 must obey or satisfy this equation, which we have here. We add our two vectors. We want to show this is in W. This is the addition of two vectors. This is the definition of vector addition in the plane. Now I need to show that this coordinate is m times this coordinate. That's what it means for this vector to be in W. Well, what is y1 plus y2? Well, we know what y1 is. That's this. We know what y2 is, that's this. And now you factor your m. So y1 plus y2 is m times x1 plus x2. That says this ordered pair satisfies this equation. That says this sum is in W. It's a simple illustration of how you go about showing those three properties about the subset W. And this is way better than showing all 10, because these are 3 of the 10 anyway. Example 2. So what is CAB? C stands for continuous function. So this is the set of all continuous functions on the closed interval AB. So now we're going to formulate a subset W. We want to show that that subset is a subspace. So let's pick a D on the interior, right? So it's not an endpoint of the closed interval AB. So D is on the interior of the open interval. Now, say we took all those functions in V, which was a continuous function on the closed interval, because that's what V is, but take just those functions where f prime of D exists. So that says f is differentiable at D using calculus terminology. We want to show such a subset of V is a subspace. Okay? So in this case, what are my circle plus and circle times? Well, those would be the circle plus and circle times in the land of V. What are those? This is the usual addition of functions and the usual scalar multiplication of functions. Proof. First, what do we want to do? We have 3 things to do. Show W is non-empty. So we have to consider the 0 function. Remember, what are the objects in my space V? These are continuous functions on the closed interval. So what is it? What is the 0 function? Well, it's the function that maps everything to 0. And of course, it's continuous on any interval, so it's certainly in V. That's not surprising. Now, is the constant function differentiable? Absolutely, it's differentiable everywhere. Therefore, f naught prime of x is 0 for all x. It's constant. Therefore, f naught prime of D exists, and of course, it's 0. So, the 0 function is in W. In other words, saying the 0 function is differentiable at D because it's differentiable everywhere. This is what we just showed. 2, we have to show that W is closed under scalar multiplication. So let's take an arbitrary function in W. We don't know what it is. The only thing we know is the one condition that it meant to be in W, that f prime, this f prime of that fixed D, that number D in the interior of the open interval, which we had here, D is fixed. Some number in between A and B. What we know is that f prime of that D exists. Okay? Now I need to show that C times f, right? That's a function, right? I need to show that it's differentiable at D. Well, of course it is. We know the calculus, and the proof is straightforward. So we know that scalar multiples can come out of the derivative, the differential operator. So C times f of D is C times f of D, and clearly this is a number. Therefore, C times f as a function is differentiable at D. Therefore, we've completed the proof of this sub-part. C times f is in W. Therefore, W is closed under scalar multiplication. Next up is addition. Okay, so now we have two arbitrary functions in W. We don't know anything about them except that they're continuous functions on the closed interval AB, and they're both differentiable at that number D. What's our goal? We need to show that f plus g is differentiable at D. Again, the derivative is a linear operator, so this will follow straight from our concepts of calculus 1. What is the derivative of f plus prime? It's f prime plus g prime. Therefore, the derivative of f plus g at D is the derivative of f at D plus the derivative at g at D. These both are numbers. Therefore, this exists. Therefore, f plus g is in W, and W is closed under addition, which means we've shown all three features, or all three properties that we needed to show. Therefore, W is a subspace of V. Using a calculus example, we've done another vector subspace proof. Remarks. I mentioned this earlier. So we use the circle plus and the circle times to represent the fact that these operations are abstract or abstracted, and they're different on each problem. In the last problem, the circle plus was the scalar multiplication of functions, and the addition was the addition of functions. 2 problems ago, the scalar multiple was the scalar multiplication in the plane, and addition was the addition of 2 ordered pairs in the plane. In this example, scalar multiplication, and vector addition were defined in terms of ordered pairs in the plane. So the point is, these will be different in terms of each problem. So for didactic purposes, I'm using circle plus and circle times to show the abstract nature of these operations. As we move forward and as we become more familiar and more mindful of the fact that these operations are abstracted and vary between problem and problem, we will drop them and use our favored notations of just times or juxtaposition and plus for vector addition. Thank you.